So good afternoon, everyone. Uh, First of all, I'd like to mention that this talk was supposed to be given by Dr. Klaus Ring from Octax, Germany, but unfortunately he's ill and he asked me to replace him today. So I'm in a difficult position because he's a physicist and very smart and brilliant mind, so it's very difficult for me to replace him and explain all his all the way he developed these lasers for IVF. So I'll try to do my best and focus the my talk on the technical aspects of the Trophectoderm biopsy. That's where we are experienced. Okay. So also, first of all, probably during my talk, I will mention many manufacturers, but I would like to clarify that neither me nor Embryo Tools, that is the company I work for, have any conflict of interest with these manufacturers, and we only provide QC tests for the IVF industry. We also run IVF training courses, and we also do training. We also do consulting services, but we don't work directly with manufacturers. Okay, so has um, all techniques have a history, and the history of the lasers for IVF started in the late 80s, beginning of the 90s, where the first experiments were performed with the lasers. These experiments were very promising, but they had a big problem. It was that the laser beams they were working with were had a very short wavelength that was near the UV light, and we all know that UV light is not good, and it induces very mutations in DNA. So after these first experiments, there was a big breakthrough that was performed by Dr. Rink in '94. He developed the first laser that was working in in the infrared range. So it was the first safe laser, let's say, for IVF procedures. Since then, this is the laser that has been used as, and is still used today with some improvements, of course. But it was a very important mark because it was the first time that safe laser could be used for IVF procedures. So these were some images from his PhD that were taken in '93. I think you can see the date in here. And this is just to show you, because we normally have the idea that we are performing holes in the zona, and actually what we are doing is a slit in the zona that it can be seen here with these images from the electronic microscopy. Okay. So as I said, after '94, this laser started being used in human IVF, and although we're talking of now, and this is a trend topic, the blastocyst biopsy, this is something that started being done in '96, where Gloria was working by that time. Institute de Cheus was one of the first centers starting doing blastocyst biopsy. And this was one of the first publications you can find about blastocyst biopsy, and it was already done in '97. But after this period, there something maybe because the culture system was not so well optimized as it is nowadays. But there was a tendency to perform biopsies on polar bodies and also on cleavage stage embryos. And now it seems that there's this movement towards pushing all of us to do trophectoderm biopsies. So why? Or some of the reasons why we consider that blastocyst biopsy is or brings advantages compared to polar body or cleavage stage biopsies is one of the reasons is that we perform we do biopsy in a few number of embryos when compared to cleavage stage or oocyte polar bodies, because we start from a court of oocytes, and some of the embryos, especially those that are chaotic, don't reach the blastocyst stage, and then we have a fewer number of embryos to do the biopsy. Also, another and very important, and also it was mentioned before by Maria Eugenia, we can get some more cells for the molecular analysis, which is important because the accuracy of the PGD or PGS results is much higher. Another possibility, another important fact is also, it was also mentioned by Maria Eugenia before, is that we increase the possibility to detect mosaicism. Another positive or another advantage of trophectoderm biopsy is that we are doing biopsy in blastocysts, though we know that these embryos at least have already developed up to this stage, and surely they are stronger than cleavage stage embryos that can after the biopsy can arrest and don't develop further. So it's also an important point. As Maria Eugenia also mentioned, there's a high within the embryos that we biopsy. We have a higher percentage of euploid because some of the chaotics, as I mentioned before, don't develop up to the blastocyst. And you will know that with blastocysts, we can have a higher potential, implantation potential, and this allows us to transfer one by one embryos with single embryo transfer and get very good results, which is also important because today it's not considered a success if we have a high multiple pregnancy rate. So the tendency is to transfer normal embryos, but one by one until the patient gets pregnant. The disadvantage of this technique, well, we have to consider that to have good blastocysts, we need a very stable culture system, and for doing this, or for ensuring that we have a stable culture system, we need well implemented quality control and quality assurance programs, and this Gloria will talk after the coffee break. Sorry. Also, to ensure this, we also need good equipment, which is sometimes expensive, and not all clinics want to invest in good equipment to provide the embryologist to have a very good lab and ensure good results, good embryos and good results. Another negative point is that for blastocyst biopsy, it's recommended to do assisted hatching on day 3 or day 4. So we cannot do an uninterrupted culture. So this is something that sometimes we forget or we cannot do because we were not advised that these embryos will be biopsied on day 5. And this is something that technically we'll see later on how to solve. Also, the trophectoderm biopsy is technically demanding, so we need to be well trained. And also, because sometimes we don't have enough time to receive the result of the molecular analysis, and we need to freeze all the blastocysts after the biopsy. So Anna will also show you how to have good results with vitrification techniques. That is very important, so we don't lose any embryo. So to do the trophectoderm biopsy, we need an inverted microscope with very good optics, because as you will see, it's important where we shoot, because we need to apply the laser shots in the cell junctions to avoid cell lysis. We also need good micromanipulators, microinjectors, anti-vibratory tables, laser system activated with a pedal, because we'll have the 2 hands occupied and in the microinjector and focusing the microscope. So it's very convenient that we have the laser activated with a pedal. We need a stereo microscope. We should use embryo test labware, and also the right size of the holding and the biopsy pipettes is also important, as you'll see in some videos later on. So in our lab we're very lucky because we have all the all the technology, the most modern technology available in the market, and this includes anti-vibratory table that is all the surface is anti-vibratory, and we can jump next to the microscope that we don't feel any vibration in the pipettes. We have also an Olympus microscope equipped with very good optics and lens. It's the EX73. We also have an electronic condenser and a synchronization box that allows us to, every time we change the lens of the microscope, the parameters of the light and contrast are adjusted automatically, so we don't need to adjust the light, and we are able to see the nuclei and the cell junctions very well, regardless whether the lens we are working with. What else? We also use microinjectors. We have both oil and air. Those that are those that we work with now are the ones with air because they're very convenient. We don't need to worry about air bubbles or refilling the deposit with oil because it's simply air and it's very good to work with. And finally, we have of course, the Octax Navi laser system that is the latest in the market, and is composed by different parts. This is the laser that is installed in the back part of the microscope. We also have the laser lens and the camera, and these the pedals I was talking about. What else do we have? This Navi system allows us to perform, well, it's a dynamic laser, so we can, with a simple mouse click, we can move the laser shot to the position we want. So in the screen of the computer we have assembled to the microscope, and we can perform multiple shots in a straight line or in a curved lines or just single shots, and this allows us to perform all these applications, since assisted hatching up to blastocyst collapsing, or testing the sperm viability, or many applications that we can do nowadays. So the techniques we normally use are the pulling and the flicking methods that we named. The pulling method is the one we use for hatching or early hatching blastocysts, that are those that have some cells out of the zona but not too many, and we call this pulling because the method is based on holding firmly the embryo with a holding pipette, and then at the same time as we pull the cells, we apply the laser shot, so we strengthen the embryo, and by this way the laser is very effective. You only need a few shots to split the cells. The good thing, or the trick in this method, is that we should shoot where the cell junctions are, so it's much easier to split or to excise the cells from the blastocyst. And that is why I mentioned before that it's important to have a good optics, because if you do this with just regular optics, you don't see where the cell junctions are, and if you shoot just in a straight line, you'll see that it's much more complicated to split the cells, because you'll have more filaments that are caused by the damage of the cells. So this is an important point. And here a video. It's not the best one, but it was the one I could take because I was advised of this talk just a few days ago. So I couldn't select too much. The first thing is to test or to feel how the embryo will behave. And so you have to gently apply some suction in the biopsy pipette and feel it and see how much suction you need to pull, which is you need to find an equilibrium, because if you suck too much, by the time you split the cells, you have the risk of losing them. So it's also very important. Another important point is the size of this biopsy pipette. If it's wider than the cluster of cells we have, it's very difficult to control them inside the pipette. So by the time you split them in here, you might lose them. So it's very important that the internal diameter of the biopsy pipette is smaller than the cluster of cells you are taking. And about the number of cells, Maria Eugenia said already, ideally we normally try to take between 4 and 8. Of course, if you take 5, it's better for you because it's easier to do you have more DNA for the molecular analysis. But yeah, you have to ensure that a minimum of 4 or 5 cells that are not lysed should be taken from the blastocyst, and not more than 10. Okay, so the other method that we also use, and we're very happy and we have very good results with, is this one that we called flicking method. That is specially indicated for fully hatched blastocysts, or for blastocysts that have a very high number of cells outside of the zona pellucida. Why? Because if they have many cells, by the time you start shooting, the embryo collapses and is very thick. So you need very high intensity pulses to split the cells, or you have to apply a high number of pulses to split the cells. And this increases the number of lysed cells. So I think with this method it's very quick, and we don't have many cells lysed, which is very good, and can be applied in almost all types of embryos. So this is based on holding the blastocyst not very firmly, just enough to hold the blastocyst, and then with 2 or 3 shots until we collapse a bit the blastocyst, so that we can take some cells inside the pipette, and then we do a flick movement between the holding and the biopsy pipette to split the cells. I'll show you a video. No, sorry. This is just to explain that the trick in this method is the position of the cells, of the needles. It's very important how we focus, and we have to make sure that we work in the same focal plane, because this is the view that we normally have, that is represented here. This is from the top, and this is from the lateral. It's very important that when you do the flicking movement, we pass with the biopsy needle through the middle point of the holding. Otherwise, we have to repeat the movement, and you have more risk of damaging the embryo and the cells. But if it's done with training, you can do it very quickly and very fast, and you don't have almost the cells lysed. So, I was saying, so you need to, this red dot corresponds to the moment where we activate the laser, and then you have to find where the junctions of the cells are and apply a first laser shot, and you'll see by the time you apply the first laser, of course every embryo behaves differently, but by the time you start applying laser shots, it will start collapsing a little bit, so we'll be able to take some more cells in the biopsy pipette. Yes, so this is done with very low intensity pulses, because we don't really need to damage the cells. We just want to mark some points so that we weak this part, and then it's very easy to do the flicking. So by the time you release the blastocyst from the holding, we focus this internal part well, you bring the same focus of the biopsy needle that you have in the holding, and then with this small movement, well, it's not small, but it's fast movement, you are able to split the cells, and after just few minutes the embryo gets back and re-expanded, and it's great. And then you can see there's almost no cells damaged, and it's very good. We're very happy with this method. These are the two methods that we use, and we can biopsy almost all embryos regardless of their developmental stage. But of course there are some problems, and always you have some difficulties because not all embryos are the same, and this is probably one of the things that is more different than day 3 biopsy, because in day 3 you only need to find the right cell that you're going to take out. But in here, because blastocysts, some collapse at the first after the laser shot, others don't collapse. Others have just few cells out of the zona. Others are still not blastocysts, so we cannot distinguish inner cell mass trophectoderm cells. Some are beautiful blastocysts, but we are not informed that we should do biopsy on them, so we need to open a hole in the zona and wait for some time until they extrude some trophectoderm cells. There's also the problem that some of them, when we did the assisted hatching on previous days, extrude the inner cell mass through this hole. So this is also complicated to do, but you'll see later on how we solve these problems. Okay. So one of the problems is this one that I mentioned before. Sometimes you have very good blastocysts expanded already, but we didn't do the assisted hatching. So for these cases, we should open a hole in the zona and wait for some hours until the blastocyst starts extruding the cells. And ideally, we should not collapse it, because every time it collapses, it wastes a lot of energy to re-expand. And it has been shown that if they take too much energy doing several collapses, then they reduce the implantation potential. So we should not or should avoid collapsing them. But this is only this sometimes is difficult. In this case, we could do it because the zona was still a little bit thick, but if it's very thin, it's very difficult to do, and the only way of doing it is collapsing it with a low intensity shot in between the cell junctions, and then open a big hole in the zona and wait until it re-expands again and it extrudes the cells. So yeah, this video was to show you the problem I was mentioning about the size of the pipettes. So when it collapses, if you see here, if we start aspirating, or if you keep on the aspirating, we have the risk of losing the cells, because we don't control inside the pipette. We don't control the suction, and it's very well, by the time they split the cells, and then we have a heart attack because we don't see the cells. But the great majority of the times the cells are inside the pipette. It's just a matter of being calm and expelling slowly until you see the cells coming out. But this can be solved if you use a smaller diameter pipette. Okay. So, and what is the ideal size of the pipettes? We normally have different ranges. We normally have stored from 20 to 30, and then depending on the degree of expansion of the blastocyst and how many cells we see or calculate there are outside of the zona, then we decide which needle we're gonna use. It's also important for the flicking method that the holding pipette is a bit more It's not rounded like in this case. It's a little bit more, how do you say? Flat, yeah. Yes. So the movement is easier, and it's easier to know exactly that we are in the right focal plane. Okay. And this flicking method is for these big guys. Many people ask us, oh, but these blastocysts are completely hatched or are almost hatched, and maybe during the biopsy they will come out of the zona. But we have to say that we have very good results also with a completely hatched blastocyst. They implant very well. We can freeze them very well. Actually, if we freeze them immediately after the biopsy when they're still collapsed, we have very good results. I think, if Anna allow me to say, the completely hatched blastocyst, the only thing different that we normally use, and maybe you can confirm if it's correct or not, but we have seen that we have very good results if when we freeze them, we vitrify them, we leave a little bit more of medium so they don't get stuck to the leaf of the cryotop. And just like oocytes, if we leave just a little bit of medium, they survive perfect, and they can be transferred without the zona. There's no risk at all. We have very good results. Thawing them, they survive, they re-expand. So this is the, sorry? And implant, yeah, sure. They implant and they give, they implant and they develop to term. And this is the method we use. Of course, the Kitasato, small volume, open system. But you can also use a closed system that's already ready in the market. And this is the last, for the last video. That is the typical case where we did assisted hatching in the previous days, but we had the bad luck that the embryo came out through the inner cell mass, and then we were getting stressed because, how can I do this? So I'll show you the video. What we normally do is that, so it works. What we normally do, and it's, for this case, it's important that we have done a big hole because it's easier for doing what we're gonna see. So we just collapse the blastocyst, okay, and then carefully we take it out of the zona, we turn it around, and we do the flicking. Really? And we have very good results, and it's just like if we had a completely hatched blastocyst. Okay. And here, obviously, we're not gonna hold the blastocyst through the inner cell mass. We just hold it next to it, so we avoid having suction in the inner cell. And then we do these few laser shots with very low intensity. We don't need to apply too much energy, although Klaus always mentioned that the intensity is not matter because we are working in a infrared wavelengths that is safe. But you see here, you take the cells there. You see you are able to count the nuclei. So in this cluster we have 8 cells, and the blastocyst is perfect. So the last thing is the tubing. That is also important because we can do everything correct, but then the last moment, if we don't place the biopsied cells correctly in the Eppendorf tube, it's like if we haven't done anything. And for doing this, we normally wash the cells in droplets without oil. I'm not sure if Maria Eugenia can tell us if it's really necessary or not. What do you think?
In our protocol, we cover with the.
You cover it all, but do you wash? Yes, yes, because in some labs I know they just take them from the droplet where they biopsy and directly put inside because yes, and they're and I think it's because they're afraid of losing the cells. But okay, so ideally we should wash them, And then we should transfer them into this Eppendorf tube that have been supplied by your molecular analysis company under the stereo microscope. And in here, to confirm that the cells are really well transferred, we should see them coming out of the capillary. So we should transfer them very carefully, slowly, and until we see that we see the cells coming out of the capillary we use for the for the tubing. And this is a small adapter that we developed because we were always feeling that we didn't have enough cells, enough hands to do all these things and focus the Eppendorf, and maybe shaking because we were nervous at the moment of doing the tubing. So we developed this adapter that holds the Eppendorf tube and allows us to have a hand free, so we are able to focus the Eppendorf at the same time that we transfer the cells. And this helps us very much. We are completely addicted to this small device. And finally, so the conclusions that I wanted to tell you is that the Trophectoderm biopsy, as we mentioned, demonstrated some beneficial um, uh, um, facts when compared to blastomery biopsy or a polar body. One of them, and the most important probably for the new techniques that are currently available, is that we can have a higher number of cells for the analysis. It's also important that we have the appropriate equipment and the correct culture system, so we are able to have good blastocysts and also have well implemented a very good cryopreservation program. And if we have these three things, we can make sure that we are able to do trophectoderm biopsies and we have good results. With these methods, the pulling and the flicking, we're able to do biopsies in almost all blastocysts, regardless of their developmental stage. It's very important that we choose the right equipment and the right tools for doing this, because it's not an easy technique, of course. And we always recommend that these techniques to be trained before in animal models until you feel confident and you can implement them in your clinical practice. Okay, thank you.